So title is a calculation of the long gamma ray burst pseudo-redshift using the Amati correlation. Okay, please start.
Okay. Good morning, everyone. Thank you for being here today. My name is Gabriela and I am an undergraduate physics student at the Universidad de San Carlos de Guatemala. And today I'll present to you this project called Calculation of Long GRBs Pseudo-Redshifts using the Amati correlation. That is a collaboration with my advisor, Dr. Rodrigo Zacaui from Universidad de San Carlos de Guatemala, Doctora Magdalena González, and Dr. Junior Perez from UNAM. Okay, I would like to start this presentation talking a little bit about gamma ray bursts. Gamma ray bursts are among the biggest explosions in the universe. They release energies up to 10 to the 55th ergs, and they are also detectable at redshifts up to 9.4 and can last from milliseconds to several minutes. They are so energetic that can outshine entire galaxies when they occur, as I show you in this GIF at the bottom. Gamma ray bursts are usually divided into main types. We have that they are divided by the T90, the T90, that is the time interval during which the 90% of the total observed count have been detected. And we have the short gamma ray bursts. They have the characteristic that their T90 lasts less than 2 seconds, and for long gamma ray bursts, we have their T90 lasts more than 2 seconds. The two main types of gamma ray bursts are also divided, also are associated with different progenitors. We have that for short gamma ray bursts, they are usually associated with the merge of compact objects, such as systems of black holes and neutron stars or neutron star. And in the case of long gamma ray bursts, we have that they are usually associated to collapsars. Usually, gamma ray bursts are described using the fireball model, in which we have a central engine, as I show you in this figure here at the bottom. We have a central engine that usually is a black hole or a highly magnetized neutron star. And it's this model has two important phases. The first one we call the prompt emission, is the initial one and the most intense part of this, because is there where the gamma rays are released, because we have particles traveling along the jet at different velocities and they are colliding with each other, and when they collide they release these gamma ripples, these gamma rays, and the energies from KEV to MeV. And this phase usually lasts only a few seconds. After this, we have another important phase that is called the afterglow. In this phase, we have that particles inside the jet start interacting with the surrounding material outside the jet, and then they cause these external shocks that emit another different radiating different wavelengths, and initially are detected in X-rays, and then we can have also emission at optical, ultraviolet, and also radio. And this phase lasts much longer than the prompt emission. Okay, the motivation for this work is we only know about 11% of the gamma ray burst we know has a redshift associated. And the measurement of the redshift, hence the distance to the sources, is essential to measuring its intrinsic properties. And since long gamma ray bursts are believed to originate from the core collapse of supermassive stars, they are powerful tools for investigate the early universe at high redshifts. Okay, due to the lack of information about the redshift of gamma ray burst, many empirical correlations have been developed in order to calculate or better understand this phenomenon. Modeling the spectra of the gamma ray burst, one of the most known correlation or is the Amati correlation, the one we're gonna use. But most of them use this empirical function that is called the band function, and they typically describe the spectra of the gamma ray burst, what we have is a broken power law. And here we have that A is a constant normalization. And we have also the E that represents the energy. We have the energy break, and also two more constant that are alpha and beta that represent the low energy index and the high energy index. Here at the bottom, I show you the typical from GRB spectrum. And we can see that these GRBs have a peak, show a peak in their spectra in the nu-F-no spectrum. And this is important because where the energy at where this peak is located is what we call the peak observed energy, and it is important for our purposes. Okay, so the correlation that we used is called the Amati correlation. It correlates the peak energy at the rest frame with the isotropic energy released by the source. And we have that is given, this correlation is given by this relation I show you here. And okay, we have that, I show you in this figure, it was inferred by using GRB with known redshift. And what Amati did is plotted different gamma ray bursts, observe the behavior, and then observe this correlation, and then he obtained the best fit, and best fit give us this constant I show you here, where this sigma is the dispersion deviation from the power law. But we can use this and do the inverse process. Since we don't know the redshift of the sample we are using, we can do the inverse process to infer pseudo redshift from this empirical correlation. As I show you here, we can obtain the peak energy at the rest frame from the peak energy observed at the spectra of the gamma ray burst. And also we can use this relation for the isotropic energy that depends on the luminosity distance and the volumetric fluence. And this correlation has a dependence on the standard cosmological model because the luminosity distance has a dependence on it. We can see that this correlation also holds when we change the isotropic energy. It means that we can have other correlations with different parameters. In this case, I will show you two more. We have, if we substitute the isotropic energy with isotropic luminosity, we can have another correlation as shown at the left side. This is known as the correlation of Ghirlanda. And also we can do it substituting the isotropic energy with the peak luminosity. As I show you on the right side, is known as the Jonoteku correlation. So why we decide to use the Amati correlation? As I showed you before in the slide before, the other correlation involved different parameters, and usually they involve more complex assumption or additional parameters that can introduce greater uncertainties. Furthermore, Amati correlation has a strong empirical support for its applicability for long gamma ray bursts, as I show you in the figure here at the right. We have a sample of long gamma ray bursts and also some extra flashes and short gamma ray bursts, but we are not going to talk about it here. We are only focused on the purple points because they represent the sample of long gamma ray bursts. As we can see, they are consistent with the Amati correlation, and here with the lines, the lines indicate the best fit and the 2 sigma confidence region for long gamma ray burst. So about the main goal of this project is use the Amati correlation to calculate the pseudo-redshift of a long gamma ray burst sample detected by the Fermi telescope. And the methods we are going to use is perform a time-integrated spectral fitting for the long gamma ray burst sample, and then obtain from the spectral fitting parameters peak energy, low energy index, and also high energy index. and perform the calculation of the pseudo-redshift for the sample. The initial sample, we select 22 high-fluence long gamma ray bursts that were detected by Fermi DBM with reported redshift. And as I show you in this figure at the right side, the data show consistency with the Amati correlation, except these two gamma ray bursts that are outside the confidence region of Amati. Okay. And we use the Amati correlation to infer the range of the redshift in which the burst is consistent, as in this example for the GRB 080916C, that we obtained an interval for the redshift, for the pseudo redshift, using the Amati correlation that is consistent with the redshift reported in the bibliography. But as we have some success cases, we also have some cases that where we can see that the Amati correlation gives us an interval that is not consistent with the redshift reported for these GRBs, as I'll show you in this at the bottom of the table. Okay, and here I show you a comparison between the redshift observed with the ratio between the pseudo redshift inferred using the Amati correlation and the redshift observed. Yeah, and we can see that this shows more or less consistency if we take into account the error bars. Okay, now let's summary and for future work. The preliminary results show consistency with the Amati correlation. Amati correlation shows consistency for a large range of redshift in our sample of 22 long gamma ray bursts from 0.2 to 5. And a combination with other methods and correlation can help us to better understand the pseudo redshift for gamma ray bursts. And for the future work, we are going to extend this work for a bigger sample of long gamma ray bursts detected by Fermi DBM, and we combine the Amati correlation with other methods and see. Thank you for your attention, and thanks to the project Puppet that make this work possible, and also the organizing committee of ISBECRI 2024.
Okay, thank you very much. We have plenty time to discuss. Are there any question or comment?
Yeah.
Sorry, I need to repeat because the people at Zoom.
Yeah, you ask why we cannot apply this for short GRBs, right?
Exactly. Thank you.
Okay. It was at the first time developed and tried to apply for all gamma ray bursts. But when they do this correlation between the isotropic energy of the source and the peak energy at the rest frame, they observe that they are not inside the best fit and the confidence region of Amati. They go outside this region, so they are not well described by the Amati correlation.
Okay, yeah. Thanks. In your last plot, I noticed that the I'm curious if you maybe have an idea of why at lower it seems to be deviating more at shorter distances. And
Yes.
I'm curious if you know this makes sense. It's I want to know if you know the origin, if or is it because we have more data there, and we have a more variability, so we have more observations, so these gamma ray bursts are more representative of all the possibilities, possible initial, possible sources.
Right now, I don't have the answer for that question, but it's a very interesting question. Maybe we can discuss it later.
Okay.
Thank you.
And one comment on my side.
Yes, I just want to contribute to that. Just it's what you were saying. We have a better sample in those redshift range. So actually, Paula is going to present another correlation method because Amati is not so good for inferring low redshift. Also, because the error bars are really high for some of the GRBs because of the spectral analysis is not so fine tuned. Yeah, but mainly it's because
But then would there be a merge between Paula's work and this work together?
yes, we actually want to try several different methods to see if we can somehow infer like a ellipsoid of redshift that are consistent with several methods. Also, we want to constrain the values of the redshift because if you see Amati, it gives error bars so big that you cannot conclude anything.
And I had a question that was a feedback to the previous one, when you were saying that you were not including short GRBs in your analysis, but I was seeing that the X-ray flashes were within the same trend as the long GRB. Do you consider them?
But in this work, we are just focusing on the long gamma ray bursts. Maybe in future work, we can take into account the X-ray flashes because they shown also a good with this correlation.
Okay.